Welcome to The Explainer. Today, we're unpacking one of the absolute most fascinating, secretive battlegrounds in all of modern computing. We're talking about the operating system's kernel, the absolute unseen core of your machine. On one side, multi-million-dollar anti-cheat development teams. On the other, incredibly sophisticated cheat syndicates pulling in just as much cash. This isn't just about video games anymore. It's a high-stakes, hyper-advanced cybersecurity arms race. Let's just jump right in.
Here's our roadmap for this explainer. First, we'll look at the endless mud fight of the kernel. Then, the hypervisor, fortress, and EPT isolation. After that, we'll cover the attacker's advanced bypass tactics, followed by software limitations and DMA invasion. And finally, we'll wrap up with the next-generation anti-cheat defense strategy.
All right, Section 1, the endless mud fight of the kernel. To truly appreciate today's security landscape, we've got to set the stage and look at the old paradigm. It was a chaotic era where both defenders and attackers fought with equal, terrifying power. So to really understand this, we need to define Ring 0, which is also known as kernel mode. Think of Ring 0 as the supreme command center of your computer. When software runs down here, it has absolute, unrestricted access to every single piece of hardware and memory on the system. This is exactly where this whole mud fight initially took place. The crazy thing is, before modern security architectures, both the game's anti-cheat driver and the malicious cheat driver were sitting right next to each other in Ring 0. It was literally a foot race. If a cheat loaded into the kernel first, it could easily blind the anti-cheat system just by directly modifying its memory or intercepting its scanning routines. Just a pure, brutal brawl of software patching. But you know, that Wild West era couldn't last forever. Let's move to Section 2, Hypervisor Fortress and EPT isolation. This was the absolute game changer that fundamentally altered the battlefield. Enter HVCI, or Hypervisor-Protected Code Integrity. Now, think of this not just as an upgrade, but as a brand new, impregnable fortress. By leveraging hardware virtualization, HVCI shifted the balance of power permanently toward the defenders. It did this by moving the rulemaking out of the vulnerable software kernel and putting it into a hardened layer right above it. With this setup, the system architecture is literally sliced in two. On one side, we have VTL 0, or Virtual Trust Level 0. This is the low-trust area where your normal Windows OS, your games, and even normal Ring 0 drivers live. But on the other side, we have VTL 1. This is the highly trusted, isolated vault. Here's the kicker. Even the highest privileged normal kernel in VTL 0 cannot peek into or modify the secure VTL 1 vault. VTL 1 acts as an untouchable judge. And that untouchable judge enforces a golden rule called the WX principle. This is managed at the hardware level by the CPU's Extended Page Table, or EPT. It brilliantly illustrates the ultimate lockdown. Memory can be writable or executable, but never, ever both. If a program tries to write dynamic code into memory, the hypervisor strictly locks out execution. If the code is allowed to execute, it becomes physically unmodifiable. Okay, so we have this hardware-level EPT lock and a secure hypervisor vault. Sounds great on paper, right? But how does this abstract architecture actually stop a cheat developer in the real world? Well, the impact is devastating for old-school hackers. The old methods of manually mapping unsigned cheat modules into memory or directly modifying an anti-cheat's code, they just fail completely. Because the hypervisor controls the hardware execution permissions, unsigned code simply cannot get execution rights. And if a cheat tries to force its way in and run illegal code anyway, boom, the system throws a massive hardware exception, resulting in an immediate blue screen of death. But hackers don't just give up and go home, right? Let's look at Section 3, Attackers' Advanced Bypass Tactics. With arbitrary code injection totally paralyzed by HVCI, let's explore their incredibly clever pivot. This brings us to a fundamental question that totally reshaped the modern cheat industry. If you literally can't run malicious code, what if you just use the code that's already there? This single thought sparked a dramatic shift to data-only attacks and the exploitation of legitimate assets. Let's walk through the Bring Your Own Vulnerable Driver, or BYOVD, attack flow. Hackers will hunt down an old, legitimately signed driver from a reputable hardware company, one that happens to have a known memory corruption bug. They load this valid driver onto the system. Because it's signed, HVCI happily lets it in. Then, attackers exploit its IOCTL handlers to gain arbitrary kernel read and write access.
From there, they use tools like KD Mapper to stealthily map cheat code directly into memory where HVCI isn't fully enforced. By dodging standard Windows loading mechanisms, they leave no official record of the driver. They're effectively turning a valid security pass into a secret backdoor. And if they're operating under strict HVCI where they truly cannot run new code, they turn to DKOM, direct kernel object manipulation. This is the ultimate stealth technique. Instead of injecting a virus, the attacker uses that vulnerable driver to manipulate the system's own management ledgers. They're altering pure data structures. They tweak handle flags to completely hide their running processes, or modify security tokens to bypass code integrity checks, all without ever executing a single line of new malicious code. It's wild. Now, anti-cheats aren't stupid. They scan the system ledgers to see if a vulnerable driver was loaded, so attackers have to clean up their mess. They'll surgically clear the PIDDB cache, totally erasing the history that their vulnerable driver was ever loaded. They'll even spoof the MU unloaded drivers list, forging internal records so that any leftover footprint looks exactly like a harmless core Windows file, like ntfs.sys. So this evolution kind of splits into two paths. On one hand, you have those data-only attacks, quietly manipulating data tokens. But on the other extreme, you have custom hypervisors. This is a ring -1 attack. The hackers actually load their own hypervisor underneath the operating system before Windows even boots. They use shadow page tables to intercept the anti-cheat scans, feeding it a fake, perfectly clean version of memory, while the actual cheat runs unimpeded in the background. It's basically a complete reality distortion field for the anti-cheat. Which brings us to Section 4, Software Limitations and DMA Invasion. We are transitioning to the absolute most extreme bypass method yet, stepping completely outside the software realm. Because look, no matter how good HVCI is, it's still a software architecture running on the CPU. Enter DMA, or Direct Memory Access Cheats. These are physical, actual PCIe hardware devices that plug directly into your motherboard. They act like an X-ray camera, reading the raw electrical signals of your RAM directly. They perfectly bypass the CPU, the operating system, and the HVCI hypervisor. The shocking reality of this DMA invasion goes like this. A gamer installs custom FPGA hardware into their motherboard's PCI slot. That hardware directly intercepts physical memory signals via the memory controller. It then sends that stolen game data out to an external, completely separate second PC. The cheat software runs entirely on that second laptop. That means there are absolutely zero malicious files, zero hooked functions, and zero traces on the gamer's main PC for an anti-cheat to find. No way, right? So, with the threat moving to custom hardware and hypervisors, how on earth do defenders respond? Let's shift our focus to Section 5, Next Generation Anti-Cheat Defense Strategy. Defenders have realized that just scanning files isn't enough anymore. To fight DMA, they are enforcing IOMMU, which uses hardware virtualization to block unauthorized PCI devices from reading memory. To fight custom hypervisors, they use anti-VMM techniques. This means they are actually measuring microscopic delays in hardware clock cycles to detect if a hidden hypervisor is slowing the system down. And finally, when the memory itself just cannot be trusted, they turn to server-side AI behavioral analysis. They analyze mouse vectors, banning players based purely on impossible superhuman reaction times. Through all of this, what you should really take away from this explainer is summarized perfectly in this quote. HVCI isn't a perfect shield. Attackers will always probe for weaknesses via BYOVD or DMA, but HVCI acts as a permanent foundational baseline. It drastically raises the marginal cost for attackers, turning what used to be cheap software hacks into incredibly expensive, highly complex hardware operations. Let's take a quick look at the timeline to recap this endless, fascinating arms race. In just over a decade, we've gone from the simple, brute force days of direct ring zero code injection through the late 2010s era of vulnerable drivers and manual mapping. Then the early 2020s brought DCOM and data-only manipulation straight into today's mind-bending reality of custom shadow hypervisors and physical DMA hardware extraction. Which leaves us with one final provocative question. We've watched the battlefield shift from software variables up into the hypervisor and now out into physical hardware and artificial intelligence. With absolute software shields bypassed by physical hardware and AI, where exactly is the next frontier for hackers? The game never truly ends, it just evolves. Thanks for joining me on this explainer, and keep your systems secure.